There is a big flaw in our best theory of the quantum world. And no, I'm not talking about the fact that it doesn't have gravity in it, which is a big problem, but rather something equally baffling. Neutrinos are fundamental particles that are part of the standard model of particle physics, which is our best description of the quantum reality. And yet, their description in the standard model does not match their behavior in the real world. In the standard model, neutrinos are supposed to be these massless particles that therefore must travel at the speed of light. However, multiple independent experiments have conclusively shown that neutrinos must have mass. And we'll come back to how we know that. But more importantly, neutrinos are among the weirdest particles we know of. They do have mass, but that mass might be coming from an entirely different mechanism to the rest of the particles. Their weird behavior may also be intimately connected to why anything exists at all, why there's so much matter in the universe but not as much antimatter. It can explain the universe and our existence in it. There are trillions of neutrinos passing through us every second, and yet we know so little about them. Almost all of a neutrino's weirdness, elusiveness comes from one simple fact. It only interacts via the weak force and, well, gravity. But gravity is a feeble interaction, especially if you are like a tiny little neutrino. At such small scales, it doesn't really have an effect. Everything that we can know about a neutrino comes from its interaction via the weak force. So practically the only way we could get anything about a neutrino is via its interaction with the weak force. And it would have been okay, only if the weak force didn't have its own little problem of sorts. Not really a problem, I mean it's a problem for us, but good that this problem exists, because without it probably we wouldn't have existed at all. We'll come to it, it will be clear. The thing about the weak force is that it only ever affects left-handed matter particles. Good, I mean left-handed people are getting their much needed recognition. But before we move ahead, since when did fundamental particles get handedness? Well, handedness for a fundamental particle has to do with something called chirality. And it would do us no better to talk about that rabbit hole. Rather, we'll talk about chirality in terms of its proxy, called helicity. It has to do with the direction of a particle's motion and the direction of its spin axis. If it is aligned, it is a right-handed particle. If it is anti-aligned, it is the left-handed particle. Why does the weak force care at all about any of this business? Well, we don't know. I mean, this feature, better known as parity or mirror symmetry, was thought to be a conserved symmetry of the universe. The universe, we thought, wouldn't care if a particle is left-handed or right-handed. And all the other interactions, strong force, gravity, electromagnetism, they conserve this symmetry. They don't care about a particle's handedness. But weak force, well, that breaks this symmetry. It treats left-hand particles very differently to right-hand particles. Actually, it breaks the symmetry to its fullest. It only ever interacts with left-handed matter particles and right-handed antimatter particles. And this one tiny thing may have allowed a universe filled with matter and not just a haze of radiation. Well, and that is a crucial difference. So far, so good. Neutrinos only interact with the weak force, and weak force only interacts with particularly handed particles. Now, where do we go from there? Well, first up, neutrinos have this mass problem. In the standard model, they're not supposed to have any mass, and yet they do have mass. How do we know that? Well, interesting. To understand why in the standard model neutrinos are massless, we'll have to look up how mass actually works down there. Particles get their mass by interacting with a field called the Higgs field. The more something interacts with the Higgs field, the more massive it is. But what is this interaction really? Well, when a particle interacts with the Higgs field, its chirality changes. A left-handed particle becomes right-handed and vice versa, and this happens continuously. This continuous mixing of handedness, chirality, is what gives the idea of mass. The more affinity something has for the Higgs field, the more this thing happens and the more massive it becomes. Now here's the problem. We've never spotted a right-handed neutrino. All the neutrinos seen so far are all left-handed. Does that mean right-handed neutrinos don't exist and all neutrinos are left-handed? Well, then they can't really change their handedness because the other hand doesn't exist. And if mass is just the eternal mixing of this handedness thing, surely they can't have mass. And this is how you end up with massless neutrinos in the standard model. On the lack of evidence of these right-handed neutrinos, remember that these can't even interact with the weak force. All the neutrinos that we've detected so far, we detect them via the weak force. But the weak force couldn't care less about right-handed particles. Surely we weren't betting on gravity to help us detect these neutrinos. Then how could we even think of detecting them? They are like just so elusive. The only way then for us to detect these right-handed neutrinos is to analyze them mixing with the kind of neutrinos that we can detect, left-handed ones. And so far there's no conclusive evidence of any right-handed neutrinos. And it might have been the general consensus that these right-handed neutrinos, famously known as sterile neutrinos, don't exist if neutrinos were massless. But they do have mass. Well, neutrinos come in three different flavors. We've all heard of the electron, but then there's also heavier cousins of electrons, the muon and the tau. These are basically similar in essence, but then just heavier. Corresponding to each of these electron-like particles, there's a corresponding neutrino. So there's an electron neutrino, there's a muon neutrino, and then there's a tau neutrino. Yeah, this time we didn't have innovative names. Together with the electron family, they make up the 6 leptons of the standard model. But well, I wasn't saying it lightly when I said that neutrinos are weird particles. If we talk about other particles, like for instance electrons, an electron, wherever it might be in a superposition of being at multiple places at once. But still then, an electron is an electron with all the properties of an electron. But the neutrinos are different. Whenever a neutrino is created, it might be in one of its flavors, but then these flavors aren't exactly independent. Rather, each of these is some combination of 3 different mass eigenstates, and as they travel, these mass states mix. And so after a while, the mass states may have moved to represent the mass states of a different flavor of neutrino. A neutrino that starts off being an electron neutrino can then turn into a muon neutrino or a tau neutrino, or then turn back to being the electron neutrino again. These are known as Neutrino Oscillations. So when a whole bunch of these neutrinos are created, either in nuclear processes here on Earth or in the Sun, we expect a certain number of them to pass through, and then we expect a certain number of them to be detected. Based on that, what we found was that we are only getting like a third of a particular kind of neutrino, essentially a consequence of neutrino oscillations. It was at that very moment when we discovered these neutrino oscillations that we knew for sure that neutrinos must have mass. This mixing of mass states could not have happened if neutrinos were massless, because they wouldn't have any initial phase difference in the mass space. I know it would have felt a lot like jargon. I didn't want to do this. And now, if that wasn't enough, the mass range of these neutrinos is at a completely different order than the mass range of other particles. So a neutrino can have a mass range of, I mean, we're not sure of it, but there are theories and there are some ideas, some experiments. The range that we have probably is around a couple of electron volts of mass. But then an electron, if you compare it with an electron, it has a mass in mega electron volts. So it's like 6 orders of difference, suggesting that maybe the way these neutrinos get mass is completely different to the way other particles get their mass. That leaves the final question. How do then these neutrinos get mass? Spoiler, we don't really know. But we do have some interesting clues. First, think of what a neutrino's antiparticle is. For a particle like electron, its antiparticle has the same mass but opposite charge. It's the positron. Crucially, the antiparticle has the opposite chirality to the regular one. The antiparticle of a left-handed object is right-handed. Now, think of how these electrons get mass. Well, they interact with the Higgs field. But this mass interaction can't turn an electron into a positron because charge needs to be conserved. However, for a neutrino, it isn't exactly clear if such a restriction is in place. Think of what a neutrino's antiparticle is. I mean, it doesn't have any nuclear charge, and it's not composed of anything smaller. Is a neutrino its own antiparticle? Everything depends upon the answer to this question. Again, spoiler, we don't know. Though there is something called the lepton number, which if conserved could make antineutrinos and neutrinos very different particles. All the matter leptons are given +1 lepton number, while all the antimatter leptons are given -1 lepton number. If lepton number is conserved, you can't just turn a neutrino to its antineutrino because, well, conservation of lepton number. However, if it's not required, if lepton number can be like violated and it's not supposed to be conserved, well then there is no problem in a Higgs-like field turning a left-handed neutrino to a right-handed neutrino, which now would be its antiparticle, because for the neutrino the only difference would then be its chirality. Let's make it simple and clear. If lepton number is conserved, antineutrino and neutrino are very different particles and you can't just convert one into another. And so in that case, if we want neutrinos to have mass, we will probably need a separate right-handed neutrino field, which would then interact with the Higgs field and the left-handed neutrino field and would land a mass. If lepton number is not conserved, well then it becomes a little bit more interesting, because then neutrino and antineutrino would be essentially the same particle looked up differently. They are then Majorana particle. A Majorana particle is a fermion that is its own antiparticle. And then there would be no problem in a Higgs-like field interacting with these neutrinos and converting them into their different-handed versions. Now, it's not a very crazy idea. Even photons are their own antiparticle, so it is theoretically plausible. There are ideas then that make neutrinos massive. The most famous one is the Seesaw mechanism. Here, the right-handed neutrinos are a lot more massive than left-handed ones, like a seesaw. If one is extra heavy, the other one's like very light. And that's important because the neutrinos, the left-handed ones that we do observe, are very tiny, very less massive. And so this mechanism can explain the fact how they have such a tiny mass. Which would then also explain why we haven't yet observed right-handed neutrinos. Because they are so massive, it requires a lot more energy for them to be created. And obviously they are very much less interacting, so that makes it even more harder for us to detect them. Luckily, there is sort of a test that can pull the lever to one side of the two possibilities. It's called the Neutrinoless double beta decay. Now, if neutrino and antineutrino are essentially the same particle and can convert into each other, what can happen is that in the rare case where there are two beta decays that have happened and there are like two neutrinos now, in the rare occurrence where the two neutrinos are anti to each other because, well, one of them can convert into another. In the rare case where they are like anti to each other, they could annihilate, and what we'll observe is like a Neutrinoless double beta decay. So far, this has never been observed, but then there are experiments in place to detect them. I should add that these are not the only ways neutrinos can have mass. I mean, there can be completely novel ways for them to have mass. But the reason all of this is interesting is because all of this mess started out because the weak force violates parity. And if neutrinos and antineutrinos are the same, they could potentially answer why we see so much matter in the universe and not a lot of antimatter. When the Big Bang happened, in an ideal, perfect world, you would expect equal amounts of matter and antimatter to be created, which could then annihilate each other, leaving behind a haze of radiation. That didn't seem to have happened, so clearly something must have caused there to be more matter than antimatter. What could have potentially happened is that the high energy conditions of the Big Bang could have led to the formation of very heavy right-handed neutrinos. And if neutrinos are Majorana particles, they can convert into each other, which can then decay into quarks and other baryonic particles. Importantly, the fact that the weak force violates parity, but more accurately it violates charge parity, which is like a bigger symmetry, that could have led to different decay rates, leading to an overall dominance of matter over antimatter. So neutrinos can potentially solve the biggest problem in physics. Why do we exist? Why is there so much matter, not as much antimatter? One other thing is that this is not the only explanation. There are other explanations, there are other ways that this could have all turned out. This is one of the ways that it could have happened. So these are all stories at this point. So this is why neutrinos are so cool. Thanks for watching.